We're going to be looking at the particle model. Keep an eye as we go through each of the sections. If your paper is highlighted in green, this means it is content you could be assessed on, while if it is in grey, this is content not on your specification. We're going to start by looking at density of materials first of all and look at a couple of methods around this. Now, first of all, the equation that we need to use here is that density is equal to mass divided by volume. Density typically is measured in kilograms per meters cubed, and if this is the case, that means mass has to be in kilograms and the volume must be in meters cubed. Notice the unit here is giving you a hint as to how to actually complete the calculation. We'll do mass divided by volume. So we've got kilograms per meter cubed in this case as our unit. Always be on the lookout that we might need to convert units. Also though, there might be an opportunity where they ask for density in grams per centimetre cubed, so it might not always be a case of unit conversions. Look at the unit they want density measured in, and you need to make sure that the mass and volume match up to this. In this question then, we've got a mass of 56 grams. That does not need to be converted, nor does the 11.2 centimetres. We're going to write down our formula. I've used the symbols here, but its density is equal to mass divided by volume, and we're going to substitute it in. So here it'll be our mass of 56 divided by 11.2, and we're going to round this to just 5. So show every step that you're kind of doing here. So in this case, if I add my units on top, it's going to be 5 grams per centimetre cubed. In this next example, an iceberg has got a mass of 11,200 kilograms and a volume of 12 metres cubed. Calculate its density. So here we're going to keep our units as they are. We'll write down our equation and we'll substitute in. So in this case, we'll have 11,200 divided by 12, which is going to give us a density of 933.333 reoccurring. If there is not an instruction in your exam about how many significant figures, you could leave it at that, but I am here going to round this to the nearest whole number, or 3 significant figures. If we have a look then, you might be asked to explain how to find the density of either a regular or irregular shaped object. My advice is use the equation. So if we need to find density, we need to find volume and we need to find mass. So to find the mass, we're going to use a balance. We'll make sure that this has been reset to 0 to make sure we don't have a 0 error in there. Because it's regularly shaped, such as a cube, will measure the length, width and height to figure out its volume. And we'll multiply those values together to find that volume. Once we know the mass and we know the volume, we can then use that in this equation to find the density, and you will get marks for this. It could be possibly a 4-mark question. So for myself, I'd always go through how I'm going to find each value. So how I'm going to find mass, how will I find volume, and then pointing out, right, I'm going to use this equation. So to find volume, we're going to use a ruler, name apparatus, say what we're going to measure. Now here there is a bit of extra detail. You might need to say that to find volume, we'll multiply length, width and height together. To find mass, name that we're measuring mass and name the equipment we'll use. So in this case, a balance. And then our final step is we'll use these values we've determined in our equation, density equals mass divided by volume. If, however, the object is irregularly shaped, so we can't measure its length, width and height to find an accurate volume, now we're going to have to do a slightly different method. Measuring the mass is exactly the same, but to find its volume, we need to use either a measuring cylinder or, in this case, a displacement beaker, sometimes known as a eureka can. So the main thing, as a bit of detail about the setup, is we'll fill this up so the water level is just below the spout. Typically, I'll have a little beaker underneath, I'll fill this up, it'll overflow slightly, and I'll then replace with a new clean beaker with nothing in. But we fill this water level just below the spout. We'll place an empty beaker below the spout, and we'll place our object in, ensuring that it's fully submerged underneath the water, and it will displace the water. we will collect and measure the volume of water that has been displaced, because this water volume here should be equal to the volume of the object. Now, an alternative method to this is you could half fill a measuring cylinder with water and record the start volume. Again, add the object, making sure it's fully submerged, and then measure the new volume and subtract the two results. So if we find our change in volume, which is our final volume, minus our start volume, we can find the volume of the object. Both of these methods are absolutely viable. You just need to be confident with which one you want to use and practice it before you go into your exam. But once we know our mass and our volume, we can then go on to use the density equation. So here, for example, we're going to say how I measure volume. So I'm going to fill a displacement beaker just up to the spout. A measuring cylinder underneath will actually give a higher resolution when we're reading this rather than a beaker. But we'll place something underneath to measure the volume. We'll add our object and collect and record the displaced water. To find the mass, we're going to use a balance, and once we have our volume and our mass, we'll use this equation, density equals mass divided by volume, and use that equation as your writing frame. So there'll be nothing wrong in saying, right, to find density, I'm going to use this equation, density equals mass divided by volume, and then you could even annotate off mass, use a balance, volume, have an arrow off, describe how you'd measure this too. Now for changes in state, we need to be able to explain what's happening to particles as we go from solids into liquids and into gases. So first of all, to be able to do this, we need to be confident with how the particles are arranged in each. So in a solid, we need these particles really closely packed together in regular kind of lines, no gaps between. With a liquid, they still need to have very few gaps between, and to kind of criticize this model, only these particles here and here are really touching. Every particle should be touching another particle with very, very few gaps at all. But you're going to start to see this random arrangement. While in a gas, you now want the particles far apart with loads of gaps and completely randomly arranged. Now there are limitations of modelling in this way, so we're showing particles as spheres and that might not be the case. So for example, carbon dioxide is made up of 3 atoms that are bonded together almost in a row. The particles are also shown as solids, and we know from atomic structure that is not the case. They show no forces between the particles. We're not really getting an idea about the 3D version of this, and we can't see if the particles are moving or how they're moving. So there are some bits and pieces been missed off these models. And we also can't tell how fast they're moving. So gases will be moving much faster than solids. But using this particle model, we can start to explain the typical properties of solids, liquids and gases. So in solids, where the particles are really close together and they vibrate about fixed positions. What this does mean though is there's not a lot of space. So the particles are really closely arranged, and as a result, solids tend to be dense. So solids are high density because the particles are really close together with little space between them. But that also explains why they're hard to compress. If compressing is the ability to squash particles close together, we can't do this because the particles are already as close as they can get. Now the shape is fixed here because actually those particles are held together with really strong forces of attraction. They can vibrate, but they're not able to move past each other, and therefore the shape of a solid is fixed. When we start to look at a liquid then, the particles are still really close together, but are able to move past each other. Critically though, they can't move away from each other. So within a liquid, the particles are vibrating and moving around actually relatively freely past each other. But liquids are going to tend to be dense because the particles are still quite close together. So liquids do have a higher density than gases because the particles are still close together with little space between them at all. And that also explains why they're quite hard to compress. Now, unlike a solid, their shape is not fixed. They're able to flow, but they will only fill the bottom of a container. Now, this is because the particles have weaker forces of attraction between them, so they can move freely past each other. but those forces of attraction are still there, so the particles can't move away from each other. So therefore they will flow, but they'll fill the bottom of that container. By the time we get to a gas, now the particles are much further apart, they're moving quickly at different speeds in all different directions. Because of the fact they're now far apart, this means that gases are not dense. We've got these large spaces between them. So gases are low density because the particles are far apart with lots of space. They can be compressed also for exactly the same reason. Now, like liquids, they will flow, but they will fill a container. They won't just go to the bottom of the container, they will fill it. Now, this is because the particles have very small forces of attraction between them now. This means they can move randomly and spread out in all directions and can move away from each other. Hence, they'll fill that container up. When we have our particles, they can change state from solid to liquid into gas. And there are two key points to be aware of. Melting point is the temperature at which substances can both melt and freeze. So it is the temperature at which solids turn into liquids, but also liquids turn into solids. And for pure water, the melting point is going to be 0 degrees. So boiling point is the temperature at which a substance turns from gases into liquids and from liquids into gases. So for water, the boiling point of pure water would be 100 degrees. Now it's worth mentioning that some substances can change straight from a solid into a gas through a process known as sublimation. What this means is that their melting point and boiling point are the same temperature. And this would apply, for example, to carbon dioxide. So different substances have different melting and boiling points, and it's all down to the forces that there are between the particles. The stronger those forces are, the higher the melting and boiling point is going to be. So what we're basically looking at is that when anything changes state, the number of particles remains exactly the same. So 1 kilogram of ice will have exactly the same mass when it's a liquid and exactly the same mass as when it's a gas, provided we didn't let any escape. So during a change in state, mass is conserved, and these are an example of a physical change. It can be reversed. Now what this does mean in chemical reactions, these are tend to be non-reversible. However, with a physical change, we can reverse it and the properties will go back to what they once were. We have this idea linked to melting and boiling point of the idea about internal energy. So when we look at particles themselves, there's energy stored within a substance. So when we talk about a system, it's an object. So internal energy is the energy stored in a system or object due to the particles that make it up. Now it is a combination of two things. It is a combination of the total kinetic energy that those particles have and their potential energy. So it doesn't matter if it's a solid, liquid or gas, the particles will be moving. They will always have kinetic energy. But also they have potential energy too. So when we look at changes of state, what we are doing is affecting the energy within the substance. So for example, here we've got particles within a solid. When we heat this, what we'd expect to see is its temperature could start to increase. Now what that would mean as the temperature starts to increase is the particles will have more kinetic energy. So the particles in the solid will begin to vibrate around more. But what we'll also see is that that's going to mean that internal energy increases. And eventually what we'll see is that this should change state. So when we heat up a system or an object, what we find is the energy inside that system increases. Now that energy increase can do one of two things. It will either raise the temperature of the object or it will cause a change in state. But those two things will not happen together. So if its temperature is changing, that's going to indicate that it is literally just increasing in temperature. But when it changes in state, there will not be an temperature change until that has stopped. So we'll either see when we heat something up, its temperature goes up, or it changes state. It will do one or the other, but it won't do both at the same time. So specific heat capacity has been visited within energy, but we're going to come back around to it here also as it fits in a bit later into the specification, around 3.22. So the temperature that a system increases by depends on a few things. It depends on the mass that actually we've been heating, the type of material that this might be, and how much energy I've put in. So what this does mean is we're now back around to using our equation for specific heat capacity. And as a definition, possibly 2 marks, this is the amount of energy that you need to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. To calculate this, we're going to use this equation here. Be careful with your calculations because this can sometimes be 5 marks. You might have to find temperature change, which might have a smaller calculation as part of it. Our energy is in joules, mass will be in kilograms, specific heat capacity they will always kind of give you the value for, but that'll be joules per kilogram degree C, and temperature change will be in degrees Celsius. So if we look at this question, we've got 200 grams of gold been heated by 10 degrees and we're told a specific heat capacity. Now the specific heat capacity has got a reference to mass in kilograms and my mass here is in grams. So we'll convert that first of all. In goes my equation and we'll then substitute. So in this case we've got 0.2 times by 129 times by 10 and therefore the energy required for this is going to be 258 joules. Now we're going to have a look at latent heat. Latent heat is the energy needed for change in state. So when we heat a substance, we can either increase its temperature, which is when we'd use our equation for specific heat capacity, or we can use it to change state. So latent heat is the energy that we need to change the state of a substance. And specific latent heat is the energy that you need to change the state of 1 kilogram of that substance without changing its temperature. So specific heat capacity is 1 kilogram of that substance increased in temperature by 1 degree, while this is now 1 kilogram of that substance changing state. Now there are 2 versions of this because we've got our melting point and boiling point. It means that for a material, it has the specific latent heat of fusion. This is the amount of energy that we need to raise or to change the state of 1 kilogram of a substance that was a solid and change it into a liquid, but have no temperature change at all. While the specific latent heat of vaporization is the energy that you need to change the state of 1 kilogram of it from now a liquid to a gas, but again notice there is no change in temperature with this, so we are just changing the state of it. For this, our equation is energy for change in state is equal to the mass times by the specific latent heat. Energy is still measured in joules, mass is in kilograms, while latent heat is in joules per kilogram. And again, that unit is indicating to us how we would rearrange the equation. If we wanted to find this, you do joules divided by mass, so kilogram. If we have a look at this example, first of all, we've got our latent heat has been given in joules per kilogram, so we'll need to convert our 500 grams of water into grams, or kilograms I should say. So 500 divided by 1000, giving us 0.5. We'll put in our equation, so energy equals mass times specific latent heat. And we'll now substitute in our values. Keep an eye out for this, because they might give you 2 values. They might give you the latent heat of fusion, which is about melting, but they could also give you a vaporization one and want you to select the right number. If you see that it's melting, use fusion. If it's evaporating, use the one of vaporization. But in this case, I'm going to need 167,000 joules to do this. In this example, we're asked to calculate the mass of water when it takes 125 kilojoules to change it from a solid to liquid, and we're given the latent heat of fusion now. So we're changing it from solid to a liquid, we're melting it. So we'll start by converting our units. Now I've got 125 kilojoules, we'll need to convert that into joules. And we'll write down our equation. So E equals M times our specific latent heat. Now we'll substitute, won't worry about rearranging just yet, and only at this point will we now rearrange to make m the subject of the equation. So it'll be that 125,000 divided by the 334,000, giving a mass of this. Again, if they haven't asked you to do any rounding, you could leave it exactly like that, or you could round to a sensible number of significant figures. I've taken 3 here because all the other values were given to 3 significant figures. Now, this graph here is going to show us typically what happens as we increase the temperature, or as we heat something, and what's happening to the temperature of that substance. So generally what we'll see, let's say this were an iodine crystal, for example. As time increases, what we're seeing as we heat it is that temperature increases. But as we continue to heat, there'll be a period of time in which actually the temperature does not change. This flat line is when actually that energy is being used to change state. And so we won't, during that state change, see a change in temperature. However, once all that substance has changed state, provided we continue to heat, what we'll see is that temperature continues to increase again. So, especially moving into the higher, there is a very big difference between specific heat capacity and specific latent heat. Heat capacity is the energy you need to change the temperature of a kilogram by 1 degree Celsius, while latent heat is the amount of energy you need to change the state of 1 kilogram, but notice there's no temperature change. So specific heat capacity has got no melting or state change. Latent heat has got no temperature change. What this does mean is that for a higher question, you should be prepared to possibly include both of these formulas or equations together. It would be grade 8, 9 through and through. Moving on to particle motion. Particles in a gas we know are arranged randomly and they move apart at different speeds and in different directions. So the molecules of a gas are in constant random motion, and that word random refers to both the direction that they're travelling in and the speed. But the temperature of the gas is linked to its average kinetic energy. So if these particles are moving faster, we're going to tend to mean that the temperature of the gas is higher. So higher temperature, the particles of the gas will have more kinetic energy, they'll move around faster. If therefore we increase the temperature of the gas, that means that pressure will increase. Pressure is down to these particles colliding with the wall. The more collisions that we've got, the higher the pressure is going to be. Be prepared in your exam to explain why the pressure of a gas increases when temperature goes up. So it's that idea that if we increase temperature, particles have more kinetic energy. They'll be moving faster around. Now, what that will mean is that particles are going to collide more with the sides of the container. So there'll be more collisions per second with that container wall. But also, the particles will be moving faster and will collide with that wall with greater force. So because we've got more collisions and those collisions are more forceful, this means that there's a greater force exerted in a given area, and therefore pressure goes up. Moving into the separate science-only content, gases can be compressed or expanded. So if we want to have a gas compressed, so particles brought closer together, or expanded, we're going to be looking at having pressure changes here. So remember, pressure is all down to the force of these collisions due to the particles on the gas container. So it's all down to this pressure itself is down to these particles colliding. If we have more collisions, we're going to see that there's more force exerted. So the more collisions, the greater that force is going to be. And the greater the force, the greater the pressure. So this definition is gas pressure is your total force per unit area. This does mean there's an equation for it. So pressure times volume will equal a constant. Pressure is measured in pascals, while volume will be measured in meters cubed. Constant doesn't have any units. So here, calculate pressure when the pressure is 10,000 Pascal in 0.03 meters cubed, and the volume is decreased to 0.025 meters cubed. So, first of all, we've got no unit conversions. We're going to find our constant. So here, pressure times volume will equal a constant, which, bit of formatting issue there, but 1,000 times 0.03, or 100,000 I should say, times by 0.03, equals a constant of 3,000. Now we've got our new volume. So what we'll then do is we'll put that new volume into our next equation. So P is now going to be multiplied by our new volume, which equals the constant that we have found. We'll rearrange this. So we'll have 3,000 divided by 0.025, giving me an overall pressure of 120,000 Pascal. So what this means is to decrease the pressure, or to decrease the volume, we've had to increase the pressure. When we do this, we do work. So work is the transfer of energy by a force, and this would just be in higher only. So when we do work on a gas, we're going to find that we increase the internal energy of the gas, and as a result, the temperature can increase. Be prepared and higher to explain why. So when temperature is higher, what we're going to find is these particles have more kinetic energy. Therefore, we're going to have more collisions with the wall, therefore more forces in a greater area, and as a consequence, the pressure will increase. Now, why does pressure increase when a gas is compressed? This is down to the fact that if we compress a gas, what we're going to find is that the volume that gas occupies has decreased. So notice we've got the same number of particles in each area, but now in this smaller area, we have now more frequent collisions between the particles and the container wall because they're occupying a smaller space. And again, it's linked to the idea that for every collision that we have is going to exert a force on this. So if we now have a smaller area and increase the number of collisions that are occurring, we're going to increase the force on the walls of the container, increasing pressure.